Hello everyone, this is my presentation to the 19th IEEE International Symposium on Network Computing and Applications. It is regarding my work related to multi-hop emergency call protocol in 5G, mHelp. First, let me ask you a question. How can you transmit emergency calls in a small local area during a network failure? There are two main technologies that can be used in such a scenario. The first one is the device-to-device technology in 4G and 5G, and the second one is the push-to-talk technology, which is the walkie-talkie technology. First, the device-to-device technology was first introduced in 4G cellular network, where there is a new physical layer design called the side link. And the side link channel is used to establish connection between two devices. In push-to-talk technology, they use a terrestrial European trunk radio technology to connect with the other devices. So these technologies are mainly deployed in local geographical areas when there's an emergency. However, in our work, we are designing the mHelp protocol where an emergency call is transmitted under a scenario where there's a large disaster impacting the network infrastructure using a self-adaptive method and a distributed protocol. This protocol is 3GPP compatible and can be developed on 4G, 5G enabled mobiles. The emergency call architecture that the mHelp protocol will be implemented is a scenario where several base stations are located in a network area and several of them get destroyed due to a large disaster striking that area. The users who are who were previously under the coverage of the destroyed base stations have now lost the connection to the network infrastructure, and due to the disaster they want to connect to the network infrastructure to transfer emergency calls to the public safety services. In order to reach the public safety services, they relay their call using intermediate relay devices to available functioning network infrastructure which are located away from the disaster location. So the mHelp protocol is working in both an emergency device and a relay device. When it is functioning in the emergency device, there's a certain algorithm that it will follow. So I will explain the algorithm. First of all, when an when a device is in and out of coverage area, it will keep listening to the control channel of the side link that is used in for D2D communications, and it will be receiving the control informations that are coming from the control channel. When an emergency call, when a person wants to send an emergency call, the phone will create a data packet including the information, emergency call ID, and emergency class identifier, localization information if available, and SINR information if available. In the next step, the call will be transmitted, and the transmission depends on two the call transmission is different when it is under coverage and when it is out of coverage. When it is under coverage, it will send the call directly to the network infrastructure using the normal procedure, using the random access channel and the physical uplink shared channel. However, when it's in the out of coverage, then it will use the side link, and since it is keeping listening to the side link control channel, it will receive the control information from other devices. So when the emergency caller is transmitting control information to other devices, the other devices will receive the control information. So the emergency call will include the specific parameters of the emergency channel that it will use to share the emergency data, and send it as the control message first, and next it will send the emergency data in the specified channel. Then during a certain fixed time of T0, it will wait and it will tune into the side link data channel and listen to all the relayings of its own emergency call relayings, but by the neighbor devices who are in the range. So if the number of relayings is NRS, and if NRS is below the relay threshold, which is defined for the mHealth protocol, then the emergency call will be retransmitted. It will be retransmitted up to a maximum limit specified for the mHealth protocol. Secondly, I will explain how the relay device functions. So the relay device will first receive a control message from an emergency first it will receive the control information of an emergency call, and next it will tune into the specified channel and then receive the emergency data. After receiving the emergency data, it will compute a waiting time parameter TR according to the equation given here. So this equation is basically dependent on three variables which are unique to each relay device. So the three variables that are taken are the location accuracy available at the relay device, and the network coverage status of the relay device, and the SOC, the state of charge or the battery level of the relay device. So these parameters are used to compute the waiting time. So the waiting time model is created such that the stronger relay devices will wait a low waiting time, and the weaker relay devices will wait a higher waiting time. During the waiting time, it will tune into the side link data channel and count the number of relayings of its own of the emergency call that it is currently processing. Let's take it as the emergency call with the ID 001, and it will count the number of relayings of 001 and take it as NRS. If the NRS is below the relay threshold, then the relay device will relay the call. This relaying will be done at the end of the waiting time TR. Next, I will explain the simulation software that I used to assess the performance of the model. So I use AnyLogic software. AnyLogic is a software which enables us to build the behavior of a single agent. So in my case, it is the mobile. So I was able to create a state diagram for the mobile, is how its behavior, and also it enabled me to create interaction links between mobiles. Next, I will explain how I developed what kind of a simulation environment I developed to assess the mHealth performance. I considered that there are 8 base stations, and because of the disaster, the base stations get distracted in the order of 1 to 7. So in the worst case scenario, only the 8 base station is functioning, and there are 100 mobile devices randomly located in the network area. The parameters that I have used for the simulation are given in this table. I considered a network area of 7.5 into 10.5 kilometers squared. Next, I will explain the evaluation parameters I used. First, the success rate. It is equal to the number of successful transmissions divided by the total number of emergency calls. Next, the average number of relayed messages per node is the total number of relayed messages in the network divided by the total number of network nodes. Thirdly, the latency. The latency is the delay of the call transmission from the emergency device to the network infrastructure. So, I will explain now the results I obtained. First, the success rate was obtained for the variation of the number of working base stations. So when the number of working base stations change, how the success rate changes. It can be seen that in the worst case scenario, when only one base station is working, about 0.53 success rate can be achieved. That means more than 50% of the calls are successfully reaching the base station from this mHealth protocol. And it can be seen that the latency of the average latency of the protocol in the worst case scenario is about 300 seconds, and the worst latency when only one base station is working is about 1800 seconds, which is about 30 minutes. It is also necessary to mention that the latency depends on the waiting time model that we developed. So the fixed parameters that we used in the waiting time model can be dynamically modeled, which is a future work of this research to optimize the latency further. So next, I observe the number of how the success rate changes with the number of emergency calls in the network. So when the number of calls are very high, more than half of the devices are under emergency state, the success rate is about 0.38. However, when it is above 50, you can reach more than 50% success rate. So that is for the worst case scenario where only one base station is working. The next graph shows how the average relayed messages per node changes with the number of calls ranging from 80 to 10. Next, I evaluated how the emergency call interval affects the success rate. When the emergency calls occur during a certain time interval, such as 5 minutes, the success rate is about 0.45. When the emergency calls occur during 1 hour time period, the success rate is about 0.66. So that means more than 50% of the calls are getting transmitted during when the emergency calls occur during 1 hour time period. So when the calls are much more spreaded during the emergency call occurring time duration, the success rate increases. And when I take the average number of relayed messages per node with the time, that means the network traffic with the time, for the emergency scenario where the calls occur for 1 hour, When I take that scenario, I can see that the network traffic increases and then reaches a certain limit without exponentially increasing. The reason for this stabilization is the addition of the parameters for network traffic controlling. The parameters added are the relay threshold and the retransmission maximum limit. So those parameters avoided the possibility of network congestion occurring. And then this figure shows how the research works related to public safety service providing are classified. In our approach, what we are trying to achieve is both network resiliency and an improvement in proximity services, specifically enhancing the D2D technologies to improve the network resiliency under a large disaster scenario. Out of the rare works, I was able to find a research work which proposed the finder algorithm, which used massive D2D mechanisms to overcome a large disaster scenario. So I used finder algorithm to compare my work. The mHelp protocol, in the finder protocol, the out of coverage, because of a large disaster, there are many out of coverage devices, and the out of coverage devices are grouped into clusters, and a cluster head is selected in each cluster. The people who want to send an emergency call will send the emergency call to the cluster head, and the cluster head will relay it further via other cluster heads to the network infrastructure. So when we compare the find algorithm and the mHelp algorithm, the control messages available in the find algorithm are higher than mHelp. The reason is in finder they create clusters and pick a cluster head using additional control messages. In mHelp, only the standard control messages used for D2D communication are used. So additional clustering or additional control messages are not used for mHelp. Second thing is, in finder the weight on one device is higher than mHelp. The reason is in clustering and in sending the emergency call only to the cluster head, they are increasing the traffic at the cluster head in a certain cluster. Apart from that, when emergency calls are coming from other clusters, the cluster head has to respond to that and relay it. So therefore, the energy consumption at the cluster head is higher than the other devices. So the weight on a particular device is higher. However, in mHelp, the traffic is dispersed uniformly around the emergency device, and only the stronger devices are relaying the call, while the weaker devices wait for a considerable time, allowing only the stronger devices to relay the call. So there's no particular weight on a certain device to relay the call. Any device can relay, however, only the stronger devices are made to relay the call further, and the traffic is dispersed uniformly. Next, I'm going to assess the performance comparison with Finder. So mHelp shows lesser network traffic compared to Finder, and the success, when I take into success rate and the average residual energy into consideration, the success rate and the average residual energy of mHelp is higher than Finder. So from mHelp, the contributions are its practicality. That means it is a realistic protocol that can be implemented in the currently available D2D technologies, rather than the theoretically proposed complex computing involved wireless ad hoc network schemes. So the feasibility of implementing it on currently available technologies is high, and from the simulations it was seen the performance was better than the find algorithm. So the reliability of the protocol is high, the simplicity of the protocol is also high. So for the future works, the dynamic modeling of the fixed parameters used for the protocol are considered, and SINR is integrated into the waiting time model. The simulation model is available in GitHub and AnyLogic Cloud in the following links. Thank you.